Properties of determinant. In the last lecture, we introduced the definition of the determinant, and we can compute determinant of any square matrix directly from the definition. In this lecture, we're going to introduce some properties, useful properties of determinant, which can make your computation simplified in some cases. So, for example, if we have 4x4 matrix of this shape, then we can use a property of triangular matrix, which says if A is a triangular matrix, then its determinant is the product of the diagonal entries. So if the matrix is given, for example, some numbers on diagonal entries and some other numbers lower part of diagonal, and everything above the diagonal entries are 0, then this is called lower triangular matrix. And opposite symmetric shape gives upper triangular matrix. So you could have some numbers like this, but everything below the diagonal will be 0. So if you have such a matrix, then you can only need to multiply the numbers in the diagonal, which gives the determinant. So we look at this. 4x4 matrix is supposed to be a long expression if you use expansion of the determinant from the definition. However, if you look at everything above this diagonal entries, that is 0, 0, 0, everything are 0. So this is lower triangular matrix. This is lower triangular. In other words, its determinant is given by multiplication of 4 numbers in the diagonal. Commutativity. We know that the product of two matrices is not commutative. In other words, usually if you multiply AB, this new matrix, AB is not equal to BA. You cannot swap two matrices in your multiplication. However, if you're only interested in determinant, then you can swap two matrices. You can change the order. So determinant AB equals determinant BA. Also, you can separately do determinant A and determinant B. So we have an example of 2x2 matrices, A and B. You can directly check the multiplication. If you multiply AB, A times B, which will not be equal to BA. I'm not going to compute that. And you can also compute determinant AB and determinant BA and determinant A, determinant B. At the end, we will find this is all negative 2. Of course, determinant A is simple. So determinant A is going to be 0 times 0 minus 1 times 1, which is negative 1. Determinant B will be 2 times 1 minus 0 times 0. So this is 2. So if the question is find determinant of AB, then instead of first do product of AB, you can directly multiply determinant A and determinant B, which gives the negative 2. Determinant after an ERO. So we learned 3 types of EROs at the beginning of the semester. So EROs, after applied, it will change the matrix. And also, it may change their determinant. Then how does one ERO change the determinant? This is concluded here. So if you swap 2 rows, then it means the determinant will be opposite. So flip the sign of the determinant. So it's the same thing as negative, or multiplied by negative 1. If you do replacement, ERO, then it will not change the determinant. If you multiply by C to one row ith row, then this is the same thing as multiplied by C to the determinant. So we will look at here. Find the determinant of 4x4 matrix. So here, at the beginning, we can see that there are many zeros. And if we rearrange, if you notice that, if you swap these two rows, R1 and R3, then the matrix, the new matrix will be 3, 0, 0, 0, and 2, 6, 3, 0. And 7, negative 2, 0, 0. And 3, negative 8, 4, negative 3. Now I'm going to do another swap. So now I'm going to change, switch these two, R2 and R3. This gives me 7, negative 2, 0, 0 in the second row, and 2, 6, 3, 0, and 3, negative 8, 4, negative 3. So after two EROs, we get new matrix from original one. So suppose this is determinant A, and this is determinant after first ERO, and this is determinant A2. Then what is determinant A2? This is easier to compute because this is lower triangular matrix. We have done this in the previous example. So if we screen those four numbers in diagonal entries and multiply them together, it gives me 54. Now, because one swap changed the sign, so determinant of A1 is opposite of A2, so negative 54. So let me put this, and this makes it is the same thing as multiplied by negative 1. And if you swap another time, then determinant A is opposite to determinant A1. So determinant A is opposite to determinant A1, which is 54. Cofactor expansion. In this property tells us that we can do expansion of the determinant along any row or any column. So in the definition, we said, for example, if we have A11, A12, A13, and A21, A22, A23, A31, A32, A33, then what you do is, by definition, you are going to screen the first row and make positive, negative, positive sign, and then expand along this row, A11 and minor of A11, and because negative sign, negative A12, minor of A12, and then A13, minor of A13. So this is the definition. Now, what in this proposition, suppose you have A square matrix. We first define ij cofactor of A, which is actually determinant of its minor times negative 1 to I plus j. So the sum of this. So this is, if I plus j is even, then this is 1. Odd, then this is negative 1. Now we can do row expansion along ith row. So determinant A is the same thing as you're expanding ith row by multiplying each entry by its cofactor. Of course, you can do column expansion, so you can go along this or go along second column. So for example, if I right? If I go along this column, then the determinant is, what I usually do is I will put their sign first. So mark the signs because this is positive, minus, and plus minus will interchange every time. So plus, minus, and plus, minus. So I make sure I have all signs for the column I want to expand. So I'm going to do second column expansion. So determinant of A is going to be negative A12, and determinant of A12. Oh, this, I forgot to write determinant here. Determinant of A11, determinant of A12, determinant of A13. And then plus determinant plus A22, determinant of A22. And then minus A32, determinant of A32. Let's look at this example. Again, 4 by 4 matrix, very similar to the previous example. If we use definition to compute the determinant, then we have to screen the first row and try to formulate the expansion. But now, what we are going to do is I'm going to identify another row which has the most zero entries. So if we look at the second row, then we have 3 entries given by 0. This 0 multiplied by anything makes 0. So this makes your computation easier. So what we do is we're going to expand the determinant using the second row. Then before we expand, we're going to identify those signs for each engine. So plus, minus, they are interchanging to each other, the signs, flipping every time. Now if I do expansion, then this is 3 times, sorry, we have to write negative sign. So because this is negative sign, so we have to write negative 1 times 3 and times determinant of its minor. So the minor is, if you delete corresponding row and column, then it becomes negative 2, 0, 0, and 6, 3, 0, negative 8, 4, negative 3. Now we move to the other entry on that row, second row. So it is plus 1 times 0 times determinant of something. But we don't care because 0 times anything becomes 0. And also the third, fourth entries always gives 0 and 0. So we have 0 items which can be totally ignored from your computation. So at the end, the determinant of this matrix is given by negative 1 times 3 times determinant of this 3 by 3 matrix, which is given by diagonal lower triangular matrix. In other words, the determinant is simply multiplication of 3 numbers. So negative 2, 3, negative 3. So I'm going negative 2, 3, negative 3. So at the end, we get negative 54. As the last example, we're going to look at one of the homework problem. So we have 3 by 3 matrix. Of course, we can do first row expansion from the definition. Then this is one way we can do. To review our properties covered in this lecture, I'm going to do a different approach. So I'm going to try to eliminate 3 and 5 from the first row. So negative 1, negative 4, negative 4, and 3, 1, 3, 5, 1, 4. And to eliminate these two numbers, I do 3 times R1 plus R2, replace R2, and 5 times R1 plus R3, replace R3. At the end, it gives me 0 here, and negative 12 plus 1, negative 12 plus 3, and 0 here, negative 20 plus 1, negative 20 plus 4, now we have 2 zeros in this column, which means I would choose this column as my expansion. And we put signs here, plus, minus, plus. Indeed, I don't care 0 entries. So the determinant, I'm concentrating on this A1, but actually replacement does not change the value of determinant. This determinant is the same as this determinant. So this is equal sign. They are equal sign in determinant. So we do determinant A. This is the same as determinant of A1. And I'm going to choose first column. So negative 1 times determinant. And if I delete first row and first column, then the rest of things negative 9, negative 19, negative 16. So negative 1 times cross multiplication, negative 11, negative 16 minus negative 9, negative 19. So the rest of thing is easy computation. All right, we stop here.